We cannot live without air. Even when swimming, we have to breathe. If we go where we can't breathe, there's a limit to how long we can stay there. Scuba divers can stay under for longer, only because they take a tank full of air with them. Air is essential for life. We breathe it in all the time. Unfortunately, in towns, it's often mixed with exhaust fumes from passing traffic. Away from the traffic, air is usually cleaner and fresher, apart from occasional farmyard smells. But even fresh air isn't one pure substance. It's a mixture of several different gases. Firstly, there's oxygen. That's the gas that's essential for life. Then there's nitrogen, which is the most common gas. Together, oxygen and nitrogen make up most of the air. The remainder is a gas called argon, small amounts of carbon dioxide, and traces of other gases such as neon. But that's not all. Mixed with air is water vapour, although the amount depends on the weather. The quantities of all the other gases remain remarkably constant. The fact that air is a mixture is used by some companies. Their business is separating the air into the different gases. It's done by cooling the air to very low temperatures when it turns into a liquid. The resulting products, in this case nitrogen, can be kept liquid and moved about in tankers. Liquid gases are so cold that they soon cool down the surrounding air, producing clouds of condensed water vapour. If the gases are to be used in smaller quantities, they're stored and transported in cylinders. So separating the gases from the air is big business. But it's not only industry that takes things from the air. What happens when we breathe? To find out, we went to see Professor Lawther of the Medical Research Council, who volunteered to act as our subject. In a carefully controlled experiment, air is breathed in from the bag on the right and out into the bag on the left. Half an hour later, the bag on the left is full of exhaled air. How does this differ from the air breathed in? We're going to look at one part, the gas carbon dioxide. To make it easier to read, the scale has been multiplied by 10, so it's indicating a level of carbon dioxide of 3.4%, far higher than in the air breathed in. The carbon dioxide is given out as part of a process which also produces energy, movement energy. Outside, on a cold winter's morning, we can actually see the final product of breathing, water. In cold weather, the water vapour we produce condenses as we breathe out. So, when we breathe, we take in oxygen and give out carbon dioxide, water and energy. Food is the final piece of the jigsaw, the fuel needed to drive the whole process. But we know the composition of the air remains the same, so what happens to the carbon dioxide that we breathe out? Here's an experiment to give us a clue. Breathing out into this flask surrounds a plant with exhaled air, rich in carbon dioxide. There's so much carbon dioxide in the exhaled air that when it's tested with a lighted splint, it extinguishes it. But leave the plant for 2 days, and it has quite an effect on the air around it. The air has become rich in oxygen. To find out how plants affect the air in this way, we need to do a group of tests. In the first, a leaf is removed from a perfectly ordinary plant and killed by boiling it in water for a few minutes. At the same time, we'll use the boiling water to heat some alcohol. Hot alcohol dissolves the colour out of the leaf. Which is now ready for testing with iodine. The leaf is turning the iodine black, indicating the presence of starch. Starch is a food made in the leaves of plants. Now for the next 2 experiments in the series. For these, we need a plant which has been kept in the dark for 24 hours. One leaf is going to be placed in air from which carbon dioxide has been removed. The air is trapped in the conical flask by sealing it with cotton wool. Carbon dioxide is absorbed by a solution of potassium hydroxide at the bottom of the flask. Another leaf is half covered with black paper. This prevents light getting to that half of the leaf. The whole plant is then left in the light for 24 hours. The leaf, deprived of carbon dioxide, was treated in boiling water and alcohol, then tested for starch with iodine. No colour change. It does not turn the iodine black. Starch is not present. This experiment indicates that leaves must have carbon dioxide to make food. The second leaf is tested in the same way. There's no starch present in the lower part of the leaf, the part cut off from the light. So leaves also need light to produce food. The last experiment in the series was done on a plant growing underwater. It gives off a gas. "24 hours later, enough gas to test. The plant gives off oxygen. So plants take in light energy and carbon dioxide and give out oxygen as they produce food. There's one more essential ingredient. Plants need water. This is the opposite of breathing. So plants restore the balance of gases in the air. Unfortunately, this balance can be upset. By combustion, the process of burning. This is petrol burning. We're using a wick of glass wool to keep it under control. Burning petrol is the driving force for most of our cars. Enormous quantities of petrol are burnt every day. But what happens when cars burn petrol? Nowadays, accurate test equipment can be used to watch everything that goes in and comes out. The petrol to drive this car comes from an external fuel tank and is carefully measured as it goes into the engine. The air is forced in by a fan because the car is stationary. But what comes out? The most obvious thing is movement, energy. Then there's the exhaust gases, one of which is carbon dioxide. The test equipment gives an almost instant measure of the level of carbon dioxide in the exhaust. Over 13%, far higher than the trace present in normal air. For the final product of burning, outside in the cold again, water vapour, condensing as it comes out of the exhaust. So, during burning, fuel and oxygen are used up, carbon dioxide, movement energy and water are produced. As we become more and more industrialised, burning occurs on a larger and larger scale. Every day a car uses up the oxygen produced by about 6 trees. And a power station, the oxygen produced by thousands of trees. The danger is that in the long term we could be altering the mixture of gases in the air.
Just go out for a breath of air and you'll be ready for Medicare. The city streets are really quite a thrill. If the hoods don't get you, the monoxide will. Pollution, pollution, wear a gas mask.
A constant check is kept on the level of pollutants, the things in the air that shouldn't be there. A sample of air from outside is drawn through water to dissolve the gases. And through a filter paper to remove the solids. Under the microscope, we can see the particles collected on the filter paper. These, for instance, are smoke particles. One way that smoke gets into the air is from domestic chimneys. It used to be much worse because nearly everybody heated their home by burning coal. Smog, very thick fog, is a danger to people, not just because of the smoke, but because of another byproduct of burning coal, a gas called sulfur dioxide. The figures for London at the end of 1952 show that the level of sulfur dioxide in smog was very high. It's no coincidence that at the same time there was a large increase in the number of deaths. It was proved that these extra deaths were caused by the combination of sulfur dioxide and smoke. So, in 1956, a Clean Air Act was passed, which made smoking chimneys of any sort illegal in most towns. In towns and cities today, the quality of the air has dramatically improved. Mind you, not that some people would notice. Smoking can produce the same effects as being in a smog every day of your life. This automatic smoking machine can puff its way through thousands of cigarettes a day. The smoke from each cigarette is drawn through a filter paper. Compare this new one with what's collected on the other filter papers. Tar. This tar would normally go into a smoker's lungs. The effect on the lungs can be measured. Healthy people should be very good at forcing air out of their lungs. For smokers and non-smokers, the results are very different. The top line shows how a smoker breathes out. The bottom line, a healthy person. The healthy person breathes out much more deeply. A smoker's breathing is very inefficient. And what about the lungs themselves? These are lung sections, thin slices of real lungs. The lung of a healthy person and a smoker's lung. The smoker's lung is full of tar. How can it possibly do its job when it's in this condition? There's no doubt smoking damages your health. If the air is to remain fit to breathe, we have to make sure that burning does not occur on such a large scale that plants are unable to restore the balance.